did not do from the beginning. So I will repeat this analysis of the same example. Okay, but we go through a complete one. Okay, basically you have an element which is a square plate. So we break down the square plate into two triangular elements, and this square plate is subjected to horizontal pull force. Supposedly you should be able to do the calculation of the northern force. Okay, we take the simple averaging. So if the right hand side along the line 2, 3 is subjected to horizontal force F, then I'm going to do the equal division. Okay, but this equal division might not be right. Okay, this equal division is wrong. You got to do the work method to find how much is the horizontal distributed force. Okay, but even if you do equal, then we shall do the simple one just to give you the okay. Okay, I will start from the original. How do you analyze this constant strain triangle? Okay, the first thing to do, I will take the example of element 1. Okay, I will now define the displacement field along the element 1. Element 1 is the one in the yellow. So how do you define this displacement domain? Okay, the displacement field can be linearly interpolated based on not 1 displacement, not 2 displacement, and not 3 displacement. So upon substitutions of the coordinate. So do convert these expressions into displacement is some coefficients multiplying the coordinate. Okay? Because this is a linear distribution, you only have x and y in the variable. Upon substituting the northern coordinate, that is x1, y1, x2, y2, x3, y3, then you can now do the substitutions and do the solution for coefficient A0, A1, and A2. All this can be done by Cramer's rule. Okay, a trick to Cramer's rule is try to find the row or column with the most zero. Okay, take for example, rather than calculating sum of 2 by 2 determinant, I will take the sum only one. Okay, 0 times something, 0 times something times b times the this displacement. Okay. So this is how you do the solution by Cramer's rule. Okay, if you want to use the MATLAB, please go back and try. You can do the inversion by MATLAB. Okay, so take for example, if you want to do the solution, you can do this by MATLAB. Okay. So you are allowed to use MATLAB for solution. Okay. And then after you have obtained the coefficients, then we substitute back into the interpolation function. So now I do the regrouping. The reason why I go through this is, this example is a right angle triangle. It's very clear cut and very clean expressions. If it's not right angle triangle, you will not have that simple expression. This simple expression is telling you, okay, the shape function, okay, for not 1 has to have contribution from u1. So you do the grouping, the shape function n1 is 1 minus x over L. X is along the length of this triangle element, and y is along the height of the triangle element. Okay, and then next, for shape function 2, that's associated with the tip of the triangle is x over L minus y over b. Okay, so okay, this is, and finally you come to u3 is multiplied with the shape function y over b. So to give you a sense, what are the shape functions? Shape function 1 will be 1 and not 1. It will be 0 at other not 2 and 3. Likewise, the shape function 2 is 1 and not 2, but 0 or not 3 and 1. And lastly, shape function 3 will be 1 at, oh, I wrote something missing. This one, it will be 1 at not 3. Okay? So it will be 0, on other nodes. OK， 你看到没有？这个带入值在其他点，如果不是这个高度是y 等于 b 的话，其他点 y 等于0 y 等于0，带入它的这个形状不会是0。OK， then next, after you have the displacement field, how do you get the strength? Okay, the strength is derivative of displacement. Okay, normal strength in the x direction is derivative of horizontal displacement with respect to x. So if you have the expression above, then you do the partial differentiation, then you get these expressions. In this case, I don't focus on the metric expressions, I will focus on the mechanics first. Okay, later we just re-express them into the matrix form. Okay, and then next, what's the normal strain in the y direction? It is del v del y. Okay, then you got to find the expression is v2 over b plus v3 over b. Okay, and lastly, the shear strain, okay, is del u over del y plus del v over del x. So the expression here, okay, is the first term, okay, but change to be v, okay, sorry, this is the one operate the partial differentiation with x is the term 2, okay, the coefficient remain the same, but it has to do with the v1, v2. Likewise for the term 1 and 2, it's a partial differentiation with respect to y, okay, so you can see the coefficient the same. So after you have the normal strain, shear strain, in terms of displacement, you can re-express them as a matrix form. The three vector of the strain, the three component strain vector is related to the displacement vector. Okay, this is 3 by 1, this is 6 by 1, and the matrix is 3 by 6. Okay, 3 means 3 row, 6 means 6 column. So the coefficient is what you obtain. Take for example, the first equation is minus 1 over L associated with U1 and plus 1 over L associated with U2. The rest of the term are 0, 0, 0. Likewise, you do the same thing of the row, second row, and you find them. Okay. And next, you must be able to calculate the stress vector. Okay. Strain is related. Stress is related to strain using the constitutive model. Okay. This constitutive model we obtained before for the plane stress. It is this expression. For the plane strain, it is another. Okay. So in this case, yeah, you must be able to do the multiplications of the constitutive model of the stiffness modulus matrix with respect to the strain vector. Okay. As a result, you got this expression. Okay. I think to many of you, this is already a challenge already. So I put the formula here. Okay, you got to use your MATLAB already. Okay, okay, so here you got to define what is B vector. Okay. Okay. Please go back and write it yourself, because in the exam time, if you need to learn MATLAB, okay, sorry, even if you have the software, you won't be able to complete the question in time. 我们来画一下。Okay, to use the MATLAB symbolic, take for example, your variable, what are the variables? You have the L, you have the V, which is a symbolic. Okay, please define L and V as a symbolic. Okay, later you might have modulus E, Poisson ratio V, okay, and thickness T. Okay, define the symbolic expression first. Okay, and then next, and then type this. Okay. So how do you type the matrix? The matrix start with a square bracket, and then each row. Okay.
you put a space, they can recognize, but you will not be, you might have typo if you put the space. So you better use the comma. Okay, this is 6 by 2. Okay, so likewise, the second row is what? Your B matrix is it 0, 0? Oh, sorry. Okay, this is it something more? Okay. Okay. 0. This is not 0 root matrix, this is the shape function. This is before. This is not right, huh? Anyway, I will try to show you, even it's not right. Okay. This is supposed to be the n map. Okay, if you are using the one with the Chinese character, then do be mindful because the minus sign there might not be recognized. This is the n map. Okay, you see that? Yeah. Adding 1 to this one. If the symbol is also including the xy, then you have to do xy there. Okay. So this is the n map. Let's see. Okay. If you now need to differentiate with respect to x, yeah, then it's something like this. Yeah, but I think you might find that they may not be right. Okay, you can just doing usual symbolic expressions. Okay, yeah, you can do differentiations. Okay, but here what we do is we do the differentiation by ourselves rather than the MATLAB. And then if you have done that, let's do the next one. Bmax is equal to, okay, we want the first character to be lowercase. Okay, this is -1 over L. 0, 1 over L, 0, 0, 0. And then for the next row, put the semicolon, and then 0, 0, 0. And then this -1 over B, 0, 1 over B. And then next row, then you go 0, comma, -1 over L. -1 over B, and then 1 over L, then 1 over B, and then 0. So in this way, then you are done with the B matrix. Okay, this is your B matrix. Okay. And then after you have done B matrix, you have to define the D matrix. What's your D matrix? Your D matrix is here. Okay, let's define what is your D matrix. Your D matrix is the expression here, E over 1 minus B squared Poisson ratio times 1B 0 semicolon B1 0 semicolon and then 0, 0, 0, and then 1 minus B divided by 2. So this is your D matrix. So you can see the the expression could be very complex. If you want to simplify it and factor out some common term, then you can do this, simplify. But I think it's too complicated. Okay, then next, what you do is you want to find the stress. The stress vector is the D matrix times the B mat. Okay? So this is how you relate. And then you want to simplify the above expression, and the above expression is answer, then you write them in this form.
好，看到没有？所以你的式子，你这个你自己去推。
And then next, how do you find out the stiffness vector? Okay, anyway, the complete expression here is obtained here. You have the B mat defined, but I purposely put the E over 1 B squared outside so that I have an expression which is clean. Okay, I don't want the multiplication to be too complicated. But then I will factor out the common factor, which is E over 1 minus B squared. Okay, and then next, how do you find the relationship between force and stiffness? We learned before. Okay, the stress times strain will give you the energy density. Okay, and if you now integrate the strain energy with respect to the volume, then you're going to get the strain energy. Okay, the final expression is strain vector times stress vector. But you know the stress vector is also D matrix times the strain vector. So if you now expand the expression of the strain vector, it is the B matrix times displacement vector. Okay, the transpose of them restricts the order of B to be the one at the back, and then U to be one at the front. So this nature of the transpose, you got to do the reordering. And then next, how do you find the nodal force? The nodal force is just partial differentiation of the strain energy with respect to the nodal displacement. If you partial differentiate it with respect to the U on node 1 or node I, then you're going to get the force on the node I in the x direction. So you can see that because you got U both at the front and the back, and this expression, even though it's complex vector and strain multiplications, but this is a scalar because this is a strain energy. 所以虽然你这个向量跟矩阵相乘，感觉上很复杂，但毕竟这个是应变的，应变的是一个存量 ，OK， 所以你微分两次，前面 u 微分一次，后面 u 微分一次，你结果得到了，我只剩下一次 u， 另外一个是 u 对 ui 的偏微分。So in this case, the expressions is an integration of partial differentiation of the displacement vector with nodal displacement times B matrix transpose times B matrix times the B matrix times the displacement vector. So you might find that this expression will be quite complex, but let's take one example. Okay, if we want to do the partial differentiation of node 1 in the x direction, then your displacement partial differentiations with u1, okay, will only give you 1 for the first degree of freedom. The rest are all 0. Okay? And then next, how about partial differentiation with respect to the y? So partial differentiation of the displacement vector with respect to the v1 will only lead to 1 as that degree of freedom. The rest are all 0. Likewise, you can do the partial differentiation with respect to the node 2 in the x directions. Only u2, okay, these partial differentiations are non-zero. Okay, let me do the corrections. The typo here. So this one is only, this term is non-zero. Okay. So you can see that for every time the partial differentiation, you got one nodal force. Okay. Why not we put this nodal force side by side? Okay. How to get this? You might find this difficult to find. Then we write one more. Okay, let's see. If you find this is difficult to write and see, then you write this. So you're taking Okay, but honestly speaking, you're summing nothing. Okay, you are doing all these expressions. Because the rest are all non-zeros. The rest are all zeros.看到没有？你的举得不熟的话，你就一项一项列。OK， 那结果你就变成这个乘上去。So in this case, you are taking every expression above and then you combine them and do the identity matrix. Okay, times this integral. This integral is BTB, thickness over the area times displacement vector. And this is what we call the base for the stiffness matrix. Okay, in this case, because you are doing the linear interpolation, okay, BTDB, okay, is just a constant. Okay, 因为你的三角形元素，它基本上是用线性做内插，所以你偏微分过后，你得到的是一个常数 B matrix，B matrix 再乘上 D 就是一个内部都是常数，不随你空间上 x y 变化，最后再乘上一次 B matrix， 所以你得到的是这幅，不好意思，乱七八糟的样子，但是你得自己去把它写成，你看得懂。Reminder, in the final examinations, even though you are allowed to use MATLAB, the marking is based on the expression. Okay, 所以你不要跟我说，老师，我用 MATLAB 算对的 ，OK， 我给你最终解。那你过程没有这个步骤，我看了最终解，对了，拿满分。那不对的话，不好意思，你没有步骤，你的步骤分就没有。So make sure you are writing your working step, even though you are allowed to use a mathematical solution. Okay, so in the end, your force vector can now be expressed as what? Your force vector can now be expressed as the integration of BTDB, thickness times area, and then times the displacement vector. Okay, so this is, okay, because of integration here, BTDB are constant. Even though you are trying to integrate over the area, okay, but the constant can be bring out of the integrations. Then what you are left is the area integration. So this is what you have. Okay, and as a result of the calculations, you'll be able to obtain this kind of stiffness matrix and displacement vector. In the case of element 1, because the not 1 are constrained, then you are able to find these expressions. Okay. So copy down the element 1 down. Okay, but clearly, you don't want to do this for every element, because every time you have to calculate the shape functions, they yeah, I'm not happy with that. Okay, so how do you do the standardized one? Okay, if you want to standardize the procedure, what you have to do is, yeah, you have to go back and take note of some equations. Okay, so this is the equation that you can copy down. Okay, then you can see that what is the stiffness matrix for the constant strain triangle. Okay, if you are doing this, okay, this is your 1, 2, 3. Make sure the sequence is counterclockwise. Okay, make sure the sequence of your notes is what you call counterclockwise. Okay, your formula here 1, 2, 3. You can start from 2, 3, 1. It can be 1, 2, 3. It can be 3, 1, 2. Okay. If you want to use this formula, make sure it is counterclockwise in order. Okay? So then your full expression can be written here. Okay, it is related to U1, V1, U2, U3, V3. So if you use this formula by clockwise order, the formula is wrong in sign. Okay? You have this some way positive, some way negative. Okay? So what is the way of solutions? How do you use the formula? Okay. To use this formula, please keep a habit of writing the notes in sequence. Not 1, 2, 3. Okay? You write them down. 1, 2, 3. Okay? The first row, second row, and third row. Okay? The expression here, y 2, 3 is read as y of the second row minus y of the third row. Okay? So this is y 2, 3. Y of the second is 0 minus y of the third. Okay? This is a 0 minus b. Okay? And then y32 is x32 is x of the third row minus x in the second row. This is L minus L0. Okay? Even though this operation is very simple, it's so simple that program can do better job than man. Okay? But for you, you make sure you're still able to do the checking. Okay? You got to write the answer, okay, in your answer script. Okay? Not let the MATLAB do the job, because I will mark your MATLAB. I will only mark your writing, your written answer. Okay? If you have all this defined, okay, MATLAB can do this pretty good job. Okay? Okay? So this is how it's done. Okay, I'm showing the second element now. Second element, you are not going to have not 1, 2, 3. You're going to have not 1, 3, 4. Okay, but please rearrange the 1, 3. Okay, this is indeed the written answer here is not. This is the right one to say. This is actually the not 1, 3, 4. But I still order them because your denotations, yeah, because of your formula. Okay. They are arranged the right order. Okay, but the symbol. So to be fair, you should say this is, if you want to change, rather than using 1, 2, 3, then you can use the RJK. Okay.
所以你们回去一定要自己练习一下。你如果手不会算，你就不要寄望 MATLAB 帮你算得准，因为没有人帮你那个检验题目，里面帮你检验这个答案。Okay, after you have the expressions, okay, usually MATLAB will give you a very complex expression. Okay, for example, I take this script and I do the substitution into MATLAB. Okay, yeah, this one is very complicated. Okay, so far for the demand is still okay, but if you are doing the multiplication, yeah, you can see that it is quite threatening, okay, or frightening, okay, but don't worry about that because, okay, for the final test, the only 3 degree of freedom will be 3 or 2 degree of freedom. You should be able to do the solution by Kramer's rule. Okay, so the expression is here. Okay, for the B matrix. Okay, then let's look at the boundary condition. In this case, the boundary condition is, okay, let's get the picture here. Yeah, because of this boundary. Because of this boundary, not 1 is fixed, not 4 is fixed. So only 3 nodes is not 3. U3, V3 are non-zero. So you only square up the related stiffness matrix. Okay? And now combine the two. This is for element 2. And the other one for element 1. These are the force balance of the free nodes. What are the free nodes? Free nodes are not 3. Above them also not 2 and not 3. So you sum up the force. Okay? So the reason why I every time say I'm not doing the stiffness assembly, I'm doing the force sum. This is the physical meaning. Your operation for the stiffness sum. Okay, but there are no physical meaning. The physical meanings in the mechanics is you can do the force sum of not 3x, not 3y. Not 3x, not 3y. Just bring this and multiply here. Okay, and do the sum. Okay? If you do that sum, see here. Okay? So you've got the expression here. And you do this force sum. The force sum here will lead to the different stiffness in the system stiffness. Okay, this is the sum. The script is there. Please go back and try it out. I included. I have uploaded this already. Then next, how do you do the solution? Okay, solution by method is this complicated expression. Okay, please go back and analyze. Okay, one way of doing that is the script could be complex, but anyway, do the division. Okay, handle the common term first, doing the factoring out. Okay. 同学，你的解答是写给老师看的 ，OK？Manet 的解答不好意思，写给机器看，你要把机器的表示方式写成你一般手算的方式 ，OK？ 要因式分解的因式分解 ，do the factoring of the term required. So, yeah. Good thing here is you might have 3 answers or 4 answers. Good thing here is your denominator in the expression are common. Yeah. So this is the kind of answer. 然后我们现在来到那个识别简单这个矩形约束 ，OK? Even though this part is not to be tested, but I still have to go through this example with you. Okay? So this is to show you that why the parametric expression is obtained. Because in this case, your displacement field is not linear. Okay? If you are having the 4 nodes, you must have 4 unknowns to find out the interpolation function. In this case, you have a constant term to express a constant trend. We have the strand that very linear along the x direction, the strand that very linear linearly in the y direction, and you have also this square term, okay, xy. Okay. As a result, when you do the substitution of nodal displacement, not 1, you're going to have the first row of the equation, u1 is equal to 1 times a0, x1 times a1, y1 times a2, x1, y1 times a3. Likewise, if you substitute in the not 2 information, u2 is equal to 1 times a0, x2 times a1, y2 times a2, x2, y2 times a3. So upon substitution, all the nodal displacement and nodal coordinate into the into the expression above, you're going to obtain the displacement vector, which is u1, u2, u3, u4. Okay? And then a 4x4 square matrix times a0, a1, a2, a3. So the first thing we're going to find out is how to find the coefficient a0, a1, a2, and a3. Okay, you express them into this displacement, into the vector, into the matrix times vector format, and then later you find a0. Okay? So in this case, the finding of the shape function will be complicated because we are going to handle 4 simultaneous equation. Then the determinant to be determined is 4x4 matrix. Okay, but luckily this is a square, this is a rectangular element. So after some simplifications, then you obtain a0 is u1, a1 is u2 minus u1 over l, a2 is u4 over minus u1 over b, and then a3 is this complicated expression u1 minus u2 plus u3 minus u4 divided by l over b. If the width of if the length of the rectangle is l and the height of the rectangle is b. So in this way, you obtain the interpolations of the displacement over 4 nodes. So this appears to be a nonlinear shape function. Okay. Indeed, this is what we call bilinear. It's a product of 2 shape functions. So you can see that u1 has a shape function of 1 minus x over l times 1 minus y over b. And then the shape function 2 for u2, okay, is x over l minus y over b. And then shape function for not 3 is x over l times y over b. And shape function for not 4 is 1 minus x over l times y over b. So 这个是双线性这个形状函数。Okay. Just to confirm, are these shape function valid? Okay? Shape function for node 1 is 1 and not 1. They are 0 on other nodes. Shape function 2 is 1 or not 2. They are 0 or all are 0. Okay? Shape function 3 is 1 and not 3. They are 0 or all other opposite nodes. And shape function 4 is 1 only on the node 4. On other nodes, they are all 0. Okay? This gives you the impression of the shape function. And then next, since you have obtained the interpolation of the horizontal displacement, you can do the same for vertical displacement. And somehow we are using the same shape functions for vertical displacement. So now the partial differentiation of horizontal displacement with x give you the normal strain in the x directions. So this is these expressions. You can do the partial differentiation of the vertical displacement with respect to y. Then you're going to get the normal strain in the y direction. Okay? And then next you can do the partial differentiation of horizontal displacement with respect to vertical coordinate plus partial differentiation of the vertical displacement with respect to horizontal coordinate. Then you obtain the shear strain. Okay? So in this way, so the expression is already very complex. Okay? Good news for you, it's not examiner, it's just for your information. Okay? 所以好消息是，这个只是给你看看，不会考。OK？ 我让你要理解一下为什么。所以 OK after you have done all the partial differentiation, list out the three strain. Normal strain in the x direction, normal strain in the y direction, plus the shear strain. And re-express them into the matrix form. The three strain vector is the B matrix times displacement vector. This B matrix has a size of 3 times 8. Because this is a rectangular element, it's got 4 nodes, each node got 2 degrees of freedom. So altogether, you have 8 degrees of freedom for one rectangular element. Okay? So you can see here, even I had done the partial differentiations, the component in the B matrix still consists of coordinate x and y, meaning the B matrix is not a constant within the element. Okay? So if you multiply this strength vector with respect to the constitutive equations, this is your so-called modulus matrix, okay, or B matrix, you're going to obtain this complex expression. Okay? Yeah. And again, the stress vector is changing within the element because you see they are depending on coordinate x and y in every term. They are not constant. Okay. Here comes the tough part. Okay. We defined strain energy before. This is a product of strain vector with a stress vector. This is a scalar. Okay. If you do the expressions of the strain vector in terms of B matrix and displacement vector, eventually you are still going to have BT dV and displacement vector and integration over the space, which is dx dy. But the problem here is D is constant, but B matrix is not a constant. It is a function of x and y. Okay? So then you have to do the integrations over the domain dx dy. Okay, anyway, let me complete the partial differentiation first before we care about the integration. Okay? The partial differentiation of this strain energy with respect to the nodal displacement is the same. They are going to give you the nodal force in the particular directions. You can do partial differentiation with ui and vi, and then eventually you are still going to have force vector equal to identity matrix times the integration of vt dv over the square domain, over the rectangular domain dx dy times the thickness. Okay, but how are you going to integrate this? This apparently is very difficult. You can do the product, doing the product of the two matrices, 8 by 3 times 3 by 8. Eventually you're going to obtain 8 8 by 8 stiffness matrix. They are still in terms of x and y. And next, in this case, rather than doing expansion fully, I first have to decide where is the free degree of freedom I have to multiply. I have to extract the free degree of freedom on node 2 and node 3. So I will choose the row 2